Alright, so let's talk about coordinate transformation. Okay. Have you guys come across any kind of coordinate transformation? No? Have you studied it all?
My bad. I gotta see what you're talking about. I gotta see it.
You like taught reflection?
Coordinate transformation.
Is it still chapter 5?
It is still chapter 4. Yeah. Coordinate transformation is
Coordinate transformation.
Yes.
where it is written.
Let's see.
Okay, so we'll start with something called fundamental notation. Okay.
So coordinate transformation.
So let's say you're trying to measure something, measure the distance of that projector from this coordinate system. So this classroom can have multiple coordinate systems. So one of the coordinate system would be z on u, x, y, and then again z, x, y. Okay. So when you measure this, the distance of this or the position vector of this, it would be different in this coordinate system and that coordinate system. You understand? So the components would be different, right?
One more time, so you, because I didn't see what you did. You did something in the corner.
So we cannot corner the coordinate system. How do you define a coordinate system? You need 3 axes and the origin. Right? So my origin is that corner. My y-axis is this axis. My x-axis is this axis.
Okay.
And z is this.
Right. And what was the other one?
Other one is the other corner.
Oh.
So if it is other corner, this would be x.
Yeah.
Okay, and that would be y. Right? You have x, y, and z. So if I am measuring the position of that, the position vector of that projector, it will be different, right? The x component would be different and y component would be different. Z component might be the same for both coordinate systems. But the x and y component are going to be different. You see it? Similarly, if I am trying to, let's say, measure the orientation of, let's say, what is z's orientation with respect to this coordinate system? How do you measure her orientation?
You got a vector going from.
These with respect to this
Coordinate system? Yeah. You can measure her position and her orientation.
From the
Orientation is which way she is facing. Okay.
So you go from the origin.
Huh?
From the
So
origin.
she's facing the.
You still have to do it from the origin, but you have to do it axis wise. Okay. So you think about it.
It's X.
X, right? How many degrees in X, how many degrees in Y, how many degrees in Z? About Z. That is how you measure orientation. You see it?
She's facing X.
So this is, see, if I am facing like this, okay? I am facing in the Y direction, right? So how do I measure my orientation? It is you measure it in right-handed sense. This angle, and this angle. Let's do it a little orientation, yes, just like position, see everything is, we're talking about degrees of freedom, okay. So there are 3 translational degrees of freedom, 3 rotational degrees of freedom. The orientation of this book, okay, this book with respect to that is, it's aligned with that frame. You see it? So for example, she is not aligned. Her orientation, she is aligned in the, so what she has done is, she has rotated how many degrees? 180 degrees about what axis?
The Z axis.
Z axis. You see it?
I don't see that she's rotated.
So if she was aligned with this frame, she would be facing like this.
Okay.
So assuming this is her x-axis, this is her y-axis. So we have to define her axis as well. So this is x-axis by y-axis, and this is z-axis. So what she has done is, she has rotated 180 degrees about z-axis. So these 2 axes are still the same. You see? So when we talk about that, so this book is now aligned with that reference frame. Okay? This would be rotation about z-axis, purely about z-axis. Okay? This would be rotation about y-axis. You see it?
Yeah.
Louis? Okay. This would be purely rotation about y-axis. This would be purely rotation about x-axis. So these are called fundamental rotations. You see? So if you are just like fundamental translation, if I'm moving only in this direction, if I'm moving in this direction, is this a fundamental translation? It's like saying I'm moving in this direction, x and y. Okay? But if I'm moving only in this direction, it's just x. It's fundamental translation. If I'm moving only in this direction, it is z. It is y. It's fundamental translation. So if I'm moving only in the vertical direction, it will be z. Okay? So there are fundamental rotations are expressed like this. So if you have think about this. This is my y, z, and my x is here, coming out. Okay? So if I rotate, fundamental rotation about x-axis, what happens?
Z becomes over.
This is y1, you can say. This is z1.
Oh, you rotate counterclockwise?
It's always right-handed sense. Right? If your x-axis is coming, this is that angle. This angle is the same, right?
Why do you have, can you explain that? Y1 and the Z1?
So if I rotate about x-axis, this y will go here. Z will become z1. Okay? Now we express, if you think about this, I can express this y1 as this component, which is
Dr. Sunny, are you rotating the entire frame on the x-axis?
you have to rotate the entire frame. So what are you rotating is you're rotating a solid object. Okay? Whenever you have a frame, it means you're rotating the object itself. So you think about this, right? What did we say? This is the x-axis. This is the y-axis. This is the z-axis. It was initially aligned with x, y, z. What I've done is, I've done this. You see it? So now this is the new y-axis. This is my new z-axis. Okay? How do you express this rotation? There's a movement, right? There's a movement in rotational movement. If you're moving this like this is translational movement. You know how to express translational movement. How do you express rotational movement? That's what we are trying to understand. Okay?
Why do we specifically choose the x-axis instead of the y-axis?
What we're doing is we'll do rotation about each of these axes. We'll do fundamental rotations. We'll do fundamental rotation about x-axis, y-axis, and z-axis. We'll do all of them. Okay? So this component is the z component, right? You can resolve these. So we'll start with this angle is phi. Okay? What is this component? I can express my y1 as
Y sine theta.
y z y1
Yeah.
y plus or y, let's call this y and y z.
That's how you express.
So what is this component, this y1? Y1 is this, okay? What is this component?
Why is he?
Oh.
This is yz. This is yz in the z direction. The magnitude is yz. The direction is z. Okay? And this component is y in the y direction. The magnitude is y. The direction is y. You see? But it also happens to be, this is can you say this is y1 sine phi y plus y1 cosine phi z? So y is what? Y is y1 into sine phi, right? You see it?
Opposite.
And this is y1 cosine phi.
Wait.
It's right angle triangle. So this is the hypotenuse, this is the cosine component, this is the sine component. What is the magnitude? The magnitude of this is y1 sine phi. The magnitude of this is y1 cosine phi. Got it?
Okay.
I don't understand the unit vectors.
Unit vector is just a direction.
In the y. So if you do y1 sine t in the y direction,
Because this, oh yeah, you're right, actually. You're right.
so
But this is actually sine, cosine. Make sense?
yeah. And that one should be signed. Cool.
You're right. Good. Very good. Now it makes sense? Okay. Now similarly, if you look at, keep in mind the XYZ, right-handed sense XYZ. That has got to be true. XYZ. Okay. That cannot change. You cannot do YXZ. Then the components will completely change. So that a right-handed sense, X, this has to be always true. When we talk about this, keep in mind, X is always Y cross Z. Y is always Z cross X. And Z is always X cross Y. Okay. So look at this, you start with X, Y, Z. Okay, and you cyclically rotate. So if you want to move Y, you move X to the last. Y cannot be X cross Z. Then Y direction will change. This has to be true, always true. When you're dealing with the right-handed sense, X, Y, Z has to be in that order. Okay. So is it in this order? So X is Y cross Z, right? Y cross Z. Similarly, so these three lines and R and Y means similarly. Okay. If you look for rotation about y-axis. Oh no, here it's not done yet. Actually, you still have Z1 as well. Okay, Z1 would be Z1. So here, see here both the components are positive. You see that? Y is in the Y direction, Z is in the Z direction. For Z, Y is in the negative Y direction. Right? If you look at this Z1, these are the components. This is ZY in the Y direction, and this is ZZ in the Z. We have Z1 sine theta in the Y direction plus V1 sine theta. This is negative. This component is negative. So if I combine this, Okay. You agree with this? So I just wrote this y1 z1, wrote it in a matrix form. These are two. You have to think about these two as two simultaneous equations. We are writing it in a matrix form. Okay. So you have cosine phi, sine phi. y1 z1 would be 1. So this is the magnitude, right? y1. y1 is the magnitude, since y1 itself is a unit vector. We started with y1 z1, all are unit vectors. So if you take the magnitude, it will just be 1. So it will be cosine phi, sine phi, minus sine phi, cosine phi. Got it? Make sense? No?
Yeah.
You understand this? Is this clear? The first one is clear. Second one is not clear yet.
I have a question in a second.
Yeah, so you might write it on this board because I can't see it because of the video. Like the bottom, like right hand.
I cannot move this here.
I'm not moving. You need my right hand on this side of the board, outside.
Sure, I'll write it on this side once for the next one.
I got some seats over there.
Huh?
I got some seats over there.
Can you use that seat, Nicholas? Can you sit there? I think that might be better for you.
You know how in the first Y1 we have a Y plus YZ? If you do that for Z1, we got split negative Z1.
Right. So this component, we are talking about this component. This is the y component, right?
Uh-huh.
Everybody agrees? This is the y component?
Yes. Negative y.
Okay?
Okay.
Negative y. Why is it negative y?
Because it's going
It's
down.
in the other direction, right? So negative z1 into sine phi. So this is z1. Right angle triangle is this. Right? This is the hypotenuse. This is the opposite side. Yes?
So are we writing y and z in terms of x and y?
First we are writing y in terms of y1 in terms of y and z. Then we are writing z1 in terms of y and z again. Got it? We are writing, what we have done is, we have started with, we are rotating an object and we want to express the rotation as a mathematical representation. Mathematically what that rotation means. Because we have to deal with rotations just like we deal with translation. You can see, Nicholas?
Yes.
This is better?
Yes.
Okay. So we are trying to give a mathematical context to it, because otherwise it doesn't make sense. If you say it is rotating, if you cannot express it mathematically, you cannot do any calculation. So we are trying to express that mathematically. That is our goal. So we have rotated something. So this is the new. What is the new orientation here? What was the original orientation?
Y and Z. And then we
So
want
yeah,
Y1.
the original orientation we express as frame x, y, z. You agree with this? It was x, y, z. The new orientation is, let's call this old, the new is x1, y1, z1. And what have we done to get to the new orientation?
Just rotate about the x-axis.
Rotated about x-axis by angle phi. Got it? Yes.
So x is the same in both lines, correct?
Yes, x is the same in both lines. I'll get to that.
So really, it could be x, y1, and z1. since X.
For completeness, what we do is we do the new this. X1 and X are the same here, but for completeness, we want to just maintain it as X1, Z1. We don't want to do X, Y1 and Z.
Okay.
But you're right, the X remains the same. X and X1 remains the same. Okay? So you get this?
So if it's a new orientation, why didn't you choose to put cosine with Y and sine with Z?
We are expressing the new orientation in terms of the old orientation. That is a relative thing, right? So how much did we rotate with respect to the old orientation? With respect to a known orientation, how much did we rotate? That's what we are trying to understand. Okay? So if I do this, if I do this, right? Or if I do like this. If you want to understand the rotation, you have to first figure out what was the old or the known orientation. When you want to express this, you have to express it with respect to the old orientation. Only then you know, because it's like something like this. I was here. You want relative position. You want my relative position. Just like that, you want my relative orientation. How that is changed. That is what we are trying to do. So that is the reason we are trying to express this. These are known quantities, right? Phi is known. Phi will be known. You will be given that angle. Okay. What you are trying to figure out is what is this new Y1 and Z1. Got it? Now, this is fundamental rotation about x-axis. Now, what we can do here is this is the two-dimensional representation, okay? Since we are dealing with space, we have to always think about 3 dimensions. Right? So this is the complete representation, complete rotational representation in 3 dimensions. So what we have done is, x1, if you see, so how you know how to calculate or how to solve this matrix, right? So what is this? Y1 will be this into this plus sine into this, right? You'll get the first equation. The second equation you'll get this into this plus this into this. You'll get the second equation. Everybody knows that, right? Here x1 is simply x. You see, x1 and x are the same, and you are actually going to get x1 is the same. See, x1 is x. No y component, no z component. Okay. Y1 does it have any x component? It will not have any x component, but it has y component. It has z component. Z1 doesn't have any x component. It doesn't have any x component. This is its y component. This is its z component. Got it? This is a fundamental rotation about x-axis by an angle phi. So this is called the rotation matrix. Rotation matrix or DCM. Direction, cosine, matrix.
Do we still look at IJK or no?
IJK is, this would be, XYZ would be IJK. So you can do that as well. That's fine as well. So this would be, you can say this is fundamental rotation about I. Okay. So what we do is we use this notation. 1 T equal to 1 0 0 0 T. So when I use this, what does this mean? This is a representation, okay? For scalars, we don't use any underline. For vectors, which are column matrices, we use just one underline. This is a rotation matrix. We use two underlines, just to differentiate it. So what you're seeing here, is the way you should read this is the rotation matrix associated with rotation about the first axis. One means first axis or z axis or I axis. By an angle phi is equal to always this.
You said rotation about the z-axis,
Rotation about one axis.
one axis.
One axis is x axis.
Right.
One is x, two is y, three is z. So similarly, if you do this, if you do the exact same process for rotation about y-axis, you're going to end up with this rotation matrix. If you do the same rotation, exact same rotation, with respect to y-axis, by an angle theta, phi theta, you change the angle just to give you a different feel. The rotation matrix, you'll end up with this rotation matrix.
So when you're doing rotation matrices, will it always be in C? Or will that letter change? Will that variable?
This is a representation, you can use C. You can use C, you can use R.
Okay. I just want to know if like that means anything special or just rotation.
It's just a rotation, it's just a, so you can, that C comes from this DC. These are all cosine, see these are all actually expressed as cosine values. Even the sine value can be expressed as a cosine value. So that's C, or you can use R.
Is there a specific reason why we change from 5 to 8 or just 5?
Just the angle. So whatever angle you rotate, so this angle will now be, will always be a numerical value when you actually do the rotation. But this has significance actually. We'll get to the significance. Okay? Yes.
Can you explain again how with the x-axis is only 1 and with y is 2? The number?
Y is also 1. That's 1.
No, I'm saying the
Oh, x is 1, 2 is y, 3 is z.
yeah. So I'm just saying that's just the notation.
That's just a notation.
Um,
1 refers to x, the first axis. X. 2 represents y.
oh, okay. I
3
thought it
represents
was
z.
something.
Yes.
What makes it a cosine matrix? Why is it called a cosine matrix?
See, all these values are actually cosines. Even this is a cosine. Every sine is a cosine. Every cosine is a sine. You should know that sine of phi is what? Cosine 90 minus t or 90 plus t.
Okay.
But in the actual thing is this is actually a cosine. Direction cosine. We studied direction cosine, right? Direction cosine. The first chapter.
Yes, we touched on it.
So it's a direction. So think about it. This is actually can be expressed as a cosine. All these are cosine. Cosine of that angle. Cosine of that angle. You can express that.
Is there ever a time that we use sine matrix, direction sine matrix?
No, we stick to direction cosine. It's actually I'll tell you separately if you want to really know why it is called a direction cosine. But there is a reason it is called a direction cosine because it is a direction cosine. Okay. But for simple explanation, think about this being expressed as every sine is a cosine, every cosine is a sine. Think about that. This can be expressed as a cosine. This can be expressed as a cosine. Right? So everything becomes a cosine. And direction cosine means something. Direction cosine means, see it's a projection. Projection is always a direction cosine. We expressed that direction cosine. Right? You remember?
Yeah, I understand what you're saying.
All projections are expressed as direction cosine. So this is, you're expressing this projection actually. What is the projection of this onto this? That is what we are really interested in. Yes.
I think I missed why the second set of matrix, the second matrix has theta versus.
It is just the angle.
Yeah, like.
So if I'm doing this, let me just write down one more, and then I'll explain to you. Okay? So you have C3 psi is equal to okay, this also should make sense to you, okay? This is rotation about z-axis by an angle psi. So you see a pattern here. It is actually very easy to remember this.
Oh, okay. So rotation method.
Yeah. If you have rotation about 1, the first column, the element in the first column, first row will be 1. The rest of the elements in the first row, first column would be 0. Then you have cosine, sine, sine, cosine. Okay? If you do it for 2, the second row and the element in the second row, second column would be 1. Then the rest of the elements in the second row, second column would be 0. You do a cosine, sine, sine, cosine. The difference is for 1 and 3, the negative sign is in the lower half of the matrix. If you see here, the negative sign is in the here. 1 and 3, the negative sign is in the lower half of that matrix. Lower half of this matrix. Lower half of this matrix. For 2, it's in the upper half. Got it?
Just cause.
If you do this, so I did this, right? If you do it for y, what happens? I'll show you quickly y. Okay? So y, if y is this, if my y is coming out here, right? This would be z, correct? This would be x, and this would be my y. Got it? Now, this would be z1, this would be x1. What is this angle? We said this is theta, this is theta. Got it? The y component is always 0 for z1, x1 and y1. Right? The y component is 0. You're seeing that here. So if you put these, y is 0. For y it is just 1. No? You seeing it? Here, y1, sorry, what is z1? cosine theta z, sorry, yeah, cosine theta z plus sine theta y, right? You agree with that? X. Yeah. Okay. And what is y1? It is minus sign, right? Huh?
X1.
This is about the y-axis.
X1 is minus sign z plus cosine x. Okay. No, it would be, see, this would be minus, okay? This would be positive. Right? It's going up still. Here both, this is positive, this is positive. Now it has to be that way. We'll do this sine x cosine z cosine theta x sine minus sine theta x. You with me?
Wait, what?
Minus
Should be
sine
minus
theta.
sine theta is
Z.
Yeah.
Okay. So you see, this is this. Okay. The y component is missing there. That means this is z. This is 0. You can write this as x1 is equal to cosine theta x plus 0 minus sine theta z. Y1 is 0 plus 1. Here it is y. Plus 0 z. You agree? You get it? Cosine sine minus, then it is 0 1 0 0 1 0, then you have sine theta 0 and you see why it is like that? And again, if you do the same thing for z, you'll get this. Okay. So this is your fundamental rotations. Now what happens if you see when you're moving, if I asked you to go to, let's say, go to that board, okay, how are you going to go to that board? Are you going to do this? Are you going to go like this? You're just going directly there, right? So similarly, when you're rotating, you don't rotate about one axis, then about this axis. You just rotate to that particular direction, that orientation. It so happens that every rotation or any rotation can be expressed as a rotation about just one axis. And that axis need not be the fundamental axis. You understand? Just like every position, every translational motion can be expressed as translational motion about x, y and z, it does not mean you translate in x, y and z, right? You just go to that point. You just directly go to that point. Okay? So similarly, rotation wise, you can just go to a rotation, which is break them up. Wake up, wake up. Okay. So when you rotate, so this rotation for example, so you understood what did we do? What our rotation was about? This axis, okay? This is x-axis, y-axis, z-axis. What if you do it like this?
You have X, Y, Z, and Z.
It will be about all three axes. Okay, this is about all three axes, but this can be expressed about a rotation about one axis and one angle, which is that axis is not one of these fundamental axes. Okay, that axis will be somewhere in between. Okay, but
when you say in between the fundamental axes, you mean like adding another plane coming out towards us on that fundamental axis?
so it will be something like this. It will be here. Okay, let's say about this. It is neither x-axis, y-axis, or z-axis. It is some combination of x, y, z. And if you rotate it about that, it will be about that axis by one angle. Okay. Now, if you want to, what we do is, here, this is something, any rotation so here it's very important that you understand what are any rotation. Any rotation can be expressed as a combination of three fundamental rotations. Any rotation, any random rotation can be expressed as a combination of three fundamental rotations. So just like any translation can be expressed as translation about three fundamental axes, any rotation can be expressed as combination of three fundamental rotations. And here rotation angles are called Euler angles. Okay? So this is EULER is pronounced as Euler. Okay? You can say Euler, yes. But don't get thrown away if somebody starts talking about Euler angles, okay, Euler rotations. It just means Euler angles. Okay? Euler was a very, very, if you get a chance, read about this person. He did so much work in his area, and see, we struggle to develop expertise even in the field of aerospace engineering. And the amount of work he has done across different streams. And he was very, very, he didn't really try to showcase his work. If somebody said, no, this is not your work, he just gave them away, saying, okay, it's not mine. So Euler did a lot of work, and one of the,
I wouldn't do that.
Yeah, that's the reason he's considered so great. He's actually some people consider him even more. Some people actually think he made much more contribution than Newton, and Newton is considered one of the most popular persons ever. I mean, don't take this in any bad sense or any negative sense. But they did a voting of who the most popular person, or who do you think about, which is most, Newton scored above Jesus Christ.
About who?
Jesus Christ. So he's considered that important to humanity or mankind.
Which is the,
Sort of like-
I believe it's more popular than Jesus Christ.
Just popularity wise, knowing the name, things like that. So that is how much he's considered to contribute, Newton. But this guy, Euler, actually made much more contribution in mathematics. He was a mathematician, purely mathematician. He did a lot of his work, whatever video games you are playing today, right? This video game is largely possible because of this guy.
He never played one.
Huh? But he never imagined that, right? His work is so fundamental, is so useful.
Just like Nikola.
Huh?
Like Nikola.
All these rotations. What your video games are is essentially all rotation matrices. Right? If you see that, they are all rotating. They are giving you perspectives all the time. If you watch football, if you watch any of the sports, there is this. They have this thing, right? What is that?
The little camera that kind of
Axis.
Yeah.
Some axis rotation they have. All that is possible because of this wonderful map. Okay. So you have to really appreciate this guy, Euler. So what he said was something very, very interesting. If you align yourself with the XYZ, the ECI coordinate frame, okay? ECI coordinate frame is x-axis is vernal equinox, z-axis is the axis of rotation, and y-axis completes the right-handed system. Okay? If you align yourself with that, and you do a 3-1-3 rotation by cap omega, I, omega angles. So what is this cap omega?
Velocity.
Cap omega is right ascension of ascending node. This is an angle, right? You looked at this orbital elements. Cap omega is one of the orbital elements. It's the right ascension of ascending node. I is the inclination. Right? Small omega is argument of periapsis or argument of perigee. So if you align yourself with the XYZ axis or the ECI frame, what is this rotation? 3 rotation by cap omega. What does that mean? Rotation about Z axis by right ascension. So you do rotation about Z axis, right ascension. Okay? And then rotation about one axis, the new one axis, do the inclination by the inclination angle. And then rotation about the new Z axis by angle cap omega, small omega. You will end up in the orbit frame, or you will end up in the orbit. You see it? What I'm saying? You have, so this is my x-axis, y-axis, z-axis. Okay? So the first rotation is about how is your right ascension defined? The angle right ascension defined. It's defined from the vernal equinox x to the line of nodes. So if I'm doing a 3 rotation, do you see right ascension happening? Do you see it now? X-axis, y-axis, z-axis. If I do a 1 rotation, if I do a 3 rotation, what does that mean? So this means C3 cap omega. C3 cap omega. You see it? Right ascension? In the right handed side, right ascension. Right? 1 rotation about inclination. Inclination is again an angle. You do 1 rotation about, so what is my new x-axis? It is about this axis now. Okay? So if I do this thing, it will become inclination.
So
Okay?
you're saying-
It is about this axis. I do this, and I do this.
Like,
Got it?
this,
Z. So since it is about this axis, so this axis will remain the same. Okay, and this. This is the XY. I'm in the Earth coordinate frame, and if I do this 3 rotations, I will go into the orbit frame. No?
I did it on triangle.
Try to visualize. So what is the orbit frame? How do you define the orbit frame? The orbit frame is your P. Orbit frame is PQW. Okay, if this is the orbit, where is my XYZ? So you can say, depending on what the inclination is. So this is my orbit frame. Okay, orbit frame is, this is P direction.
Seems like X is in the major axis direction. So,
Right, so let's say this is Earth. Okay. This would be my Z direction. Okay. This would be X direction. This would be Y direction. Depending on, so here it depends on how this Earth is oriented. Okay. You have to think about this Earth. If you have this, the orbit can be like this. Orbit can be like this. Orbit can be like this. Okay?
That's inclination, right?
Huh?
That's inclination.
Right, that is the inclination means inclination of the orbital frame with respect to the equatorial frame. But there is this angle as well. You have to understand these angles as well. What are these angles? Cap omega and I. Okay. So if you just think about this, if I want to get into the orbit frame is defined as, just erase this. Just like the ECI frame, we define P as the direction of the periapsis. W is in the direction of angular momentum. Okay? So W is defined as this direction because the motion is this way. So Q will be simply, this is F, this is Q. And this is W. Alright? PQW. PQW is generally called the orbit frame, or it's simply called PQW frame. It's also called perifocal frame. If you want to go from ECI frame to the perifocal frame, you do a 3-1-3 rotation.
In a rotation, you're not covering any distance, you're only rotating, right? So, with like my pen, it'll be like open, turn that way, up, and that's over. Right?
It will be 3 rotations. So, this is my orbit frame and ECI frame are aligned. Okay, so I do a 3 rotation here. X-axis, Y-axis, Z-axis. I do a first rotation about X-axis. Then the new rotation is about first rotation is about Z-axis. Z-axis. Second rotation is about X-axis, 1,
And it
3,
doesn't
1,
matter
3.
which way. Doesn't matter which way. Like,
It's positive,
oh, okay.
right-handed sense. Okay, here also it is right-handed sense. This is the direction of Z-axis, right-handed sense, right? Right-handed sense. This is the new X-axis. X has changed, Y has changed, but Z is the same direction, right? So about new axis it will be, so this will remain where it is. Now it is this, I have to do the rotation about Z axis. So this is the ECI frame. When I do this, and this is the orbit.
So you rotate about Z twice.
You rotate about Z twice. But it's the new Z axis. Because when you do this, Z does not change. Okay? Z is in this direction, right? But when you do the next rotation about one axis, your Z will be like this. Your Z has changed. And then you do again right-handed sense. So you're going from, if this is my equatorial plane, if I do 3, 1, 3, this is my orbit.
Okay.
So this plane is my orbit. This plane was my equator.
Okay.
If I do 3, 1, 3, this is my orbit.
Okay. I didn't want to see the visualization.
So these angles are define the orientation. So these are orbital elements. Okay, these are orbital elements, right? These are 3 orbital elements out of the 6 orbital elements we talked about. Right ascension of ascending node, inclination, argument of periaxis or argument of perigee. These are the angles, and we are rotating by that angles. You see it? Any questions? Guys are good? Guys are good? Be prepared for Thursday?
Is it just going to be on Thursday?
Huh? No, it's just chapter 2. Yes. Chapter 2.